Picture this. You're standing on a beach at night, looking up at the stars. The sky stretches endlessly above you, and your brain tries to comprehend the scale of what you're seeing. But here's the thing, your brain can't actually do that. Not really, because the universe operates on scales that evolution never prepared us to understand. And today, we're going to explore one of the most mind-bending concepts in all of science, the light year. Now, a lot of people think a light year is a measure of time. It's not. And that's actually the first hint that we're about to enter territory where our everyday intuition completely falls apart. A light year is a distance. Specifically, it's the distance that light travels through the vacuum of space in 1 year. And let me tell you, that distance is so incomprehensibly vast that it rewires how you think about the universe. Let's start with something we can actually grasp, the speed of light. In the vacuum of space, light travels at approximately 186,282 miles per second. For our friends using the metric system, that's about 300,000 kilometers per second. Now that's fast, insanely fast. If you could somehow ride a beam of light and zoom around Earth's equator, you'd circle the planet about 7.5 times in just 1 second. Light is, as far as we know, the ultimate speed limit of the universe. Nothing with mass can ever reach it. Nothing can exceed it. It's the cosmic speed limit set by the fabric of space-time itself. This is not just theory. This is not just some mathematical abstraction. This is a fundamental law of physics that has been tested billions of times and never violated. Einstein discovered this in his theory of special relativity back in 1905, and it revolutionized our understanding of space, time, and energy. The equation E equals mc squared that came out of that theory is the most famous equation in the world, and it shows us that mass and energy are interchangeable. That's the power of understanding light speed. But here's where things get weird. Because light is so absurdly fast, we don't typically measure cosmic distances in miles or kilometers. Those numbers become incomprehensible. Instead, astronomers use light years. And when you really think about what that means, it's kind of beautiful and terrifying at the same time. Imagine you're sending a signal across space at the speed of light. If you send it to the sun, it takes about 8 minutes and 20 seconds to get there. That's why when you look at the sun, you're seeing it as it was 8 minutes and 20 seconds ago. The sun you see is already ancient history. And our sun is right here. It's our closest star. Well, technically, the closest star is Proxima Centauri, but let's talk about the sun first because it helps establish the scale. 8 minutes of light travel time to the sun doesn't sound like much, but let me put it in perspective. The fastest spacecraft humanity has ever created is the Parker Solar Probe. It was designed to study the sun, and it gets incredibly close. At its closest approach, it travels at about 364,000 miles per hour. That's faster than you'd ever think something could go. And yet, if we sent the Parker Solar Probe directly toward the sun at its top speed, it would still take about 13.5 hours to get there. Light does it in 8 minutes and 20 seconds. Light is about 98 times faster than our fastest spacecraft. Think about that. We've launched the fastest thing humans have ever created, and light still makes it look like it's standing still. That's how dramatic the difference is between the speeds we can achieve and the speed of light. Now, let's expand our view a little bit. The outer edge of our solar system, where the Oort cloud sits, is about 100,000 times farther from the sun than Earth is. That's roughly 9.3 trillion miles. And light takes about 16 hours to travel that distance. Our entire solar system, every planet, every moon, every comet, all of it, is inside what we could call a 16-hour light bubble. Within that bubble, we've sent a handful of spacecraft. The Voyager 1 spacecraft, which has been traveling through space since 1977, is still in the solar system. After more than 40 years of travel, it hasn't even reached the Oort cloud yet. It won't reach the edge of the solar system for another 30,000 years. And meanwhile, light would cross that same distance in 16 hours. When you zoom out past that, when you leave the solar system and look at the nearest stars, that's where light years become essential. Because the nearest star system to Earth, Proxima Centauri, is 4.24 light years away. What does that mean? It means that the light we see from Proxima Centauri today started its journey toward us over 4 years ago. When that light left Proxima Centauri, Barack Obama was still president. That star is so far away that light, moving at 186,000 miles per second, takes more than 4 years to cross the space between us. Let's really sit with that number for a moment. 4 years. That's 1,460 days. That's 35,040 hours. That's over 2.1 billion seconds. And in those 2.1 billion seconds, light, the fastest thing in the universe, is still only covering the distance between us and the nearest star. And here's where your brain starts to break, because 4 light years is the closest star to us. The next closest star, Sirius, is 8.6 light years away. Then there's Procyon at 11.4 light years. And as you look deeper into the galaxy, the numbers get increasingly absurd. But wait, there's more. Because Proxima Centauri isn't just randomly the closest star, it's actually in a triple star system. Proxima Centauri is the small red dwarf, and it orbits at a distance with 2 other stars, Alpha Centauri A and Alpha Centauri B. Those 2 stars are slightly farther away than Proxima, but still incredibly close in cosmic terms. And here's what makes this even more interesting. Proxima Centauri might have planets around it. In fact, we've detected at least one planet, called Proxima Centauri b, and that planet might be in the habitable zone. It might be able to support liquid water on its surface. So the closest star to us, just 4.24 light years away, might have a potentially habitable planet, and yet we can't reach it. With our current spacecraft, it would take about 75,000 years to get there, and we'd have no way to send messages back and forth. Any conversation with beings on Proxima Centauri b would require 8 years of waiting just for the initial message to arrive and the reply to come back.
This is the fundamental problem that light years represent. They're not just numbers, they're barriers. They're the cosmic distance that separates us from the rest of the universe. Let's talk about a few more famous stars that you might actually recognize from the night sky. Betelgeuse, that red supergiant in the Orion constellation, the one that marks the shoulder of the hunter in the winter sky. It's 640 light years away. The light entering your eye from Betelgeuse tonight left that star when Columbus was sailing across the Atlantic Ocean. When humans were just beginning to explore our own planet, that light was beginning its journey across the galaxy toward us. And Betelgeuse is a special case because it's a supergiant star, which means it's absolutely enormous. It's so big that if you placed it where the Sun is, its surface would extend out past the orbit of Jupiter. It's one of the largest known stars in the galaxy, and it's getting old, very old. Astronomers have been watching Betelgeuse because it's likely to go supernova within the next few thousand years. When it does, it will be bright enough to see during the day. The explosion will be visible without a telescope. It will be one of the most spectacular astronomical events that humans could witness. But here's the thing. When that supernova happens, the light from it will take 640 years to reach us. We won't see the explosion for centuries. And by the time we see it, the explosion will have already happened. The star will have already begun to collapse and disperse. We'll be seeing the most spectacular event in astronomy, but we'll be seeing it 640 years after the fact. And Betelgeuse is not even that far away in cosmic terms. It's relatively close. It's in our own galaxy. It's in the Milky Way. Speaking of the Milky Way, let's get some perspective on our home galaxy. The Milky Way is a spiral galaxy, and it's about 100,000 light-years across. 100,000 light-years. Let me just say that again because I want it to sink in. Our home galaxy, the galaxy containing billions of stars, all of the mythology and history and astronomy we've studied for thousands of years, all of it fits inside a structure that's 100,000 light-years wide. If you were to traverse the Milky Way from one edge to the other, traveling at the speed of light, it would take you 100,000 years. For context, 100,000 years ago, anatomically modern humans were just beginning to spread across Africa. The last ice age was still going strong. Neanderthals walked the earth. Woolly mammoths roamed the frozen tundra. And if you tried to travel across the galaxy in a straight line at the speed of light, it would take longer than all of recorded human history to make the crossing. Light, the fastest thing we know of, takes 100,000 years to traverse our home galaxy. Just let that sink in. The fastest possible speed, the cosmic speed limit, still requires 100,000 years to traverse our home galaxy. Now, the Sun is located about 26,000 light-years from the galactic center. The Sagittarius A star black hole at the center of the Milky Way is so far from us that if we sent a signal traveling at light speed toward it, it would take 26,000 years to arrive. The light from that region of space that reaches us today started its journey during the Stone Age. When it arrives at our telescopes, it tells us about light that left a massive black hole in the distant past, information that's nearly as old as human civilization. And here's something that most people don't think about. We can actually observe that black hole. Sagittarius A star is a supermassive black hole with a mass equivalent to about 4 million suns. It's one of the most massive objects in the entire galaxy, and yet we can see it. We can observe it with radio telescopes. We can watch how stars orbit around it. We can see the effects of its gravity on the surrounding gas and dust. And all of that information has been traveling for 26,000 years to reach us. The Event Horizon Telescope, a global network of radio telescopes, actually imaged the black hole at the center of a nearby galaxy called Messier 87. They created the first direct image of a black hole, and it was one of the most stunning achievements in modern astronomy. The light from that black hole traveled across 55 million light-years of space to reach our instruments. But here's something even more mind-bending. We can't even see the other side of our own galaxy clearly because of all the dust and gas in the way. Our view of the universe is limited. We can see far backward in time. We can see deep into space, but we can't see everywhere equally clearly. The galaxy obscures itself. The dust clouds block our view of many regions. We have to use infrared telescopes and radio telescopes to look through the dust and see what's hidden. We have to be creative and use different parts of the electromagnetic spectrum to explore. And that's just our galaxy, just the Milky Way. There are about 200 billion to 2 trillion galaxies in the observable universe. Yes, you read that correctly. Astronomers' estimates have been refined over time, and with instruments like the James Webb Space Telescope, they've realized there might be far more galaxies than previously thought. The universe is more crowded with galaxies than we ever imagined. But let's use 200 billion as a working number, because even that is almost incomprehensible. 200 billion galaxies. Each of those galaxies contains billions or sometimes hundreds of billions of stars.
The total number of stars in the observable universe is estimated to be around 24 septillion. That's 24 followed by 24 zeros. There are more stars in the universe than there are grains of sand on all of Earth's beaches. And to measure the distances between galaxies, even light years isn't enough. We have to use megaparsecs. 1 parsec is about 3.26 light years. A megaparsec is a million parsecs, which is about 3.26 million light years. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light years away. The light we see from Andromeda today left that galaxy when early humans were just beginning to craft tools in Africa. Andromeda has about 1 trillion stars in it, 1 trillion. And it's so far away that light takes 2.5 million years to cross the space between us. When we look at Andromeda through a telescope, we're seeing it as a snapshot of a galaxy as it was 2.5 million years ago. We're seeing it as it was when Australopithecus roamed the savannas of Africa. We're seeing ancient history written in starlight. And even more wild than that, Andromeda is approaching us. We're on a collision course. The Andromeda Galaxy is moving toward the Milky Way at about 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide and merge into a single galaxy. This won't be a disaster for life on Earth. The distances between stars are so vast that the probability of two stars actually colliding is almost zero. But it will be a cosmic event of unimaginable proportions. When the two galaxies collide and merge, they'll interact gravitationally. Stars will be flung into different orbits. Gas clouds will collide and form new stars. The center of the newly merged galaxy will become active, possibly triggering bursts of star formation and energetic phenomena.
The night sky will change dramatically, if there are humans around to witness it. If our species has survived that long, they'll see a completely different universe. And the light from that cataclysmic event will take millions of years to reach observers in other galaxies. The universe operates on timescales that make even the age of our solar system look trivial. But we're not done, not even close. The Virgo cluster, a collection of about 1,300 to 2,000 galaxies, is about 64 million light years away. The light from the nearest galaxies in that cluster that reaches us today began its journey when the dinosaurs still roamed the Earth. 64 million light years is a distance so vast that our fastest spacecraft would take billions of years to traverse it. The Virgo cluster contains some of the largest and most interesting galaxies in the nearby universe, including the Sombrero Galaxy, with its distinctive disk and dust lane, and M87, the galaxy famous for harboring the black hole that the Event Horizon telescope imaged. The Coma cluster, another galaxy cluster, is about 300 million light years away. The Hercules supercluster is about 1 billion light years away. And if you keep going, keep pushing deeper and deeper into space, you eventually reach what we call the observable universe. The observable universe, and this is a crucial distinction, is not the entire universe. It's just the part we can see. The universe might be infinite. We simply don't know. But the observable universe has a radius of about 46.5 billion light years.
Wait, you might ask, how can the observable universe be bigger than 13.8 billion years across if it's only 13.8 billion years old? That's because the universe has been expanding. When light from distant objects began its journey toward us in the early universe, space itself was expanding rapidly. The universe has been expanding since the Big Bang, and it's been accelerating in that expansion. When light from the most distant objects began its journey toward us in the early universe, space itself was expanding faster, in some cases, than light could travel. So while light from the most distant objects only needed about 13.8 billion years to reach us in terms of proper time, the objects themselves have receded much farther away in that same time due to cosmic expansion. Space itself is stretching, carrying distant galaxies with it. It's like they're on a rubber sheet, and that sheet is being pulled and stretched. The farther apart two points are on the sheet, the faster they move away from each other. This is one of the most counterintuitive concepts in all of cosmology, and it's crucial to understanding what light years actually mean in the context of an expanding universe. The light year is a static measure of distance. It's the distance light travels in 1 year in the vacuum of space.
But the universe itself is not static. The space between galaxies is expanding. The most distant object we've ever observed is a galaxy called GNZ11, which is about 13.4 billion light-years away in terms of light travel time, but is now estimated to be more like 33 billion light-years away due to cosmic expansion. When that light left GNZ11, the universe was less than half its current age. We're seeing this galaxy as it was when the universe was just a baby, before stars had finished forming in the way they do today. And here's what really breaks your brain. If you could somehow instantly teleport to that galaxy today, ignore the physics for a moment and just imagine, you'd find that the light from our sun, the light that's been traveling for the entire 13.4 billion years, wouldn't have even started its journey yet. The universe is expanding so fast that the distance between us and the most distant observable objects is growing faster than light can travel. We're essentially in a cosmic game of catch-up, where we'll never catch up. We see these distant galaxies, but we might never be able to reach them. The expansion of space itself prevents it. They're receding from us at speeds that exceed the speed of light. And Einstein's theory of general relativity actually allows this, because they're not moving through space faster than light. Rather, space itself is expanding between us, carrying them away. Think about it this way. Imagine you're standing on a balloon, and someone is slowly inflating the balloon. You're standing on a marked point on the balloon. As the balloon inflates, the point you're standing on doesn't move relative to the balloon's surface, but it moves away from other points on the balloon's surface. The more air is pumped in, the faster it moves away from other points. That's essentially what's happening in the universe. Space itself is the balloon, and matter is painted on the surface of the balloon. So when we talk about distances in the universe, we're not just talking about how far away things are right now. We're talking about the distance light had to travel to reach us, which is different from where those objects actually are in the current moment. The universe is weaving together space, time, distance, and expansion in ways that defy our evolutionary intuition. Let's talk about what this means for our understanding of the cosmos. We can divide the universe into several zones based on light travel distance. There's our local solar system, which is about a light year in diameter. There's our local stellar neighborhood, which extends about 50 light years and contains about 100 stars.
There's the Milky Way, which is 100,000 light-years across. There's the local group, which is a collection of galaxies, including the Milky Way and Andromeda, extending about 10 million light-years across. Then there's the Virgo supercluster, which contains the local group and about 100,000 other galaxies, extending about 110 million light-years across.
Then there's the observable universe, extending about 46.5 billion light-years in all directions. Each of these zones represents a different scale of cosmic organization, a different way of understanding where we are. And as you move from one zone to the next, the numbers get larger and more incomprehensible. Now, let's think about what this means practically. If there's intelligent life out there in the galaxy, in some other solar system, orbiting some other star, how would we ever communicate with them? Let's imagine there's a civilization 50 light-years away. We send them a message. They don't receive it for 50 years. They read our message and send a response. We don't receive their reply for another 50 years. A single exchange of information takes 100 years. If there's intelligent life 500 light-years away, you're looking at 1,000 years for a back-and-forth conversation. A civilization 5,000 light-years away? 10,000 years per exchange. Meanwhile, in those 10,000 years, entire civilizations on Earth rise and fall. Languages change. Governments collapse. The people having the conversation will have been dead for centuries, and their descendants might not even remember why their ancestors started trying to talk to the stars. This is why many scientists believe that if we ever encounter extraterrestrial intelligence, we'll probably just observe them from afar. We might detect their transmissions. We might even see evidence of their existence. But real-time conversation across the stars might be impossible. The universe itself enforces isolation through distance and time. And that raises a profound question. If we can't easily communicate across light years, if the distances are so vast that light itself, the fastest thing in the universe, takes millions or billions of years to cross them, what does that mean for humanity's place in the cosmos? What does it mean for our dreams of spacefaring civilization? Let's put our fastest current spacecraft in perspective again. The Parker Solar Probe travels at about 430,000 miles per hour. That's faster than anything humans have ever created. But the nearest star is 4.24 light-years away. At the Parker Solar Probe's speed, it would take about 73,000 years to get there. And that's just to the nearest star. If you wanted to travel to the center of the galaxy, 26,000 light-years away, at the Parker Solar Probe speed, it would take roughly 180 million years. For context, the dinosaurs went extinct 66 million years ago. Mammals have only been around for about 200 million years. Birds descended from theropod dinosaurs. Humans have only been around for about 300,000 years, and traveling at the speed of our fastest spacecraft to the galactic center would take almost as long as all of mammalian history, and we still wouldn't be at the edge of the galaxy. But here's something important. We don't have to physically travel to distant parts of the universe to explore them. We have light. Light brings information to us. We can study distant galaxies by analyzing the light that left them billions of years ago. We can understand the composition of distant stars by analyzing the light they emit. We can detect planets around other stars by looking at how their light flickers as planets pass in front of them. Light is our messenger, our window into the cosmos. Part 3. Light as information. Light carries enormous amounts of information. When light from a star reaches our eyes or our telescopes, it tells us several things. First, it tells us that the star exists and where it is in the sky. Second, by analyzing the spectrum of the light,
Breaking it down into its component colors, like a prism makes a rainbow, we can determine what elements are in the star. We can see the fingerprints of hydrogen, helium, carbon, oxygen, and every other element. This technique is called spectroscopy, and it's one of the most powerful tools in astronomy. A star's spectrum can tell us not just what it's made of, but how hot it is, how fast it's moving toward us or away from us, whether it's rotating, and countless other details. All of this information comes from light that's been traveling light years of space. And we can go even deeper. We can look at the specific absorption lines in a star's spectrum, the places where light at certain wavelengths has been absorbed by atoms in the star's atmosphere, and we can determine not just what elements are present, but how abundantly present they are. We can measure the temperature, density, and composition of the star's atmosphere with remarkable precision, all from analyzing light that traveled billions of miles to reach us. When we look at distant galaxies, we can do the same thing. We can analyze the light from an entire galaxy and determine how many stars it contains, how fast it's rotating, whether it's heading toward us or away from us, and whether it's actively forming new stars.
We can literally read the story of a galaxy's life written in its light. And here's where it gets really fascinating. We can use the light from distant galaxies to measure distances. When astronomers want to measure the distance to a galaxy, they often use a technique called the cosmic distance ladder. This is a series of methods that build on each other to measure greater and greater distances. For the closest stars, we use parallax. We measure the position of a star relative to distant background stars. Then, 6 months later, Earth has moved to the other side of its orbit around the Sun, and we measure the star's position again. The nearby star will have appeared to shift its position relative to the distant background. This shift is called parallax, and it allows us to calculate the distance to the star. Once we know the distances to nearby stars, we can determine their true brightness. Some of these nearby stars are related to more distant stars, and we can use those relationships to determine the brightness of more distant stars. One particularly useful type of star is the Cepheid variable. These are stars whose brightness varies in a regular, predictable way. By measuring how bright they appear and knowing their true brightness, we can calculate their distance. And we can see Cepheid variables in other galaxies. Edwin Hubble used Cepheid variables to measure the distance to Andromeda in the 1920s, and he discovered that Andromeda was far beyond our own galaxy. This was a revolutionary discovery that expanded our universe from a single galaxy to a universe of galaxies. As we push to greater distances, we use other techniques. We look at the brightness of supernovae, particularly type 1a supernovae, which have a consistent peak brightness that allows us to calculate their distance. We look at the relationship between a galaxy's brightness and how quickly it rotates, which gives us another way to measure distance. We use the brightness of the brightest stars in distant galaxies. And as we push to the very limits of the observable universe, we use the light from the cosmic microwave background radiation, the afterglow of the Big Bang itself. This light has been traveling for about 13.8 billion years, and analyzing it tells us about the structure and composition of the entire universe. All of these techniques depend on the fact that light carries information across vast distances. We're not just seeing light from distant objects, we're seeing information about the structure, composition, motion, and history of the universe. When you look through a telescope at a distant galaxy, you're not looking at where that galaxy is now. You're looking at where it was billions of years ago. The universe is so vast, and light travels so slowly compared to those distances, that the present moment is separated from distant objects by billions of years of travel time. Think about that.
Everything you see in the night sky is ancient.
The light from the sun is 8 minutes old. The light from Proxima Centauri is 4 years old. The light from Andromeda is 2.5 million years old. The light from distant galaxies is billions of years old. When you look up at the stars, you're looking at a cosmic history book. Every photon entering your eye is a message from the past. And here's the kicker. We can actually use this to our advantage. By looking at galaxies at different distances, we can see the universe at different ages. We can watch how galaxies evolved. We can see how stars formed. We can trace the history of the universe just by looking at different points in space. Because different points in space mean different points in time. Light years, therefore, are not just a measure of distance, they're a measure of look-back time. They're cosmic timestamps. They're the way the universe keeps its records and tells its story. Astronomers have used this principle to study how galaxies have changed over cosmic time. When we look at nearby galaxies, we see them as they are today. When we look at distant galaxies, we see them as they were billions of years ago. By comparing nearby and distant galaxies, we can see the history of how galaxies change and evolve. We've discovered that the universe has gone through different phases. In the early universe, shortly after the Big Bang, there were fewer large galaxies and more small, chaotic galaxies. Over time, galaxies merged together, grew larger, and became more organized. Star formation rates have changed over time. The overall structure of the universe has evolved. All of this knowledge comes from the light that's been traveling toward us through space and time. Now I want to talk about something else that light years help us understand: the vastness of cosmic voids. Space is not evenly distributed. Galaxies cluster together, pulled by gravity. But between these clusters are enormous empty regions called voids. Some of these voids are hundreds of millions of light years across. Just empty space, no galaxies, just darkness. The Boötes void is one of the largest known voids in the universe. It's about 330 million light years across. In that entire region, there are far fewer galaxies than you'd expect. It's a cosmic desert. And its size is so vast that light itself takes 330 million years to cross it. There are other large voids as well. The void in Canes Venatati is about 250 million light years across. The local void, which is relatively nearby, is about 250 million light years from the Milky Way. There's the giant void, which is appropriately named because it's enormous. When you think about voids that large, you realize that the universe isn't just big, it's incomprehensibly big, dramatically big, almost offensively big. The scale is so far beyond our ability to visualize that we have to use numbers and mathematics just to even have a conversation about it. And those numbers are humbling. They're meant to be humbling. Because when you realize that our entire solar system is less than a light year in diameter, that our fastest spacecraft would take tens of thousands of years to reach the nearest star, that galaxies are separated by millions or billions of light years, that the observable universe extends for 46.5 billion light years in all directions, when you really internalize those numbers, something shifts in your perspective. You realize that the universe is vast beyond comprehension. You realize that humanity, for all our achievements and all our intelligence, is incredibly tiny and limited by the cosmic speed limit. You realize that we're confined to a small corner of an almost incomprehensibly large cosmos. But here's where it gets interesting, because we've discovered something remarkable about the structure of the universe. It's not randomly distributed.
Galaxies aren't scattered haphazardly through space. Instead, they form a cosmic web. Galaxies cluster along filaments like pearls on a string. These filaments are separated by vast empty voids. If you were to map the universe on the largest scales, showing every galaxy within 1 billion light-years or so, you'd see a structure that looks almost organic. It looks like a cosmic web or a foam, with dense regions and empty regions. This structure developed in the early universe through the action of gravity. Tiny variations in the density of matter in the early universe got amplified by gravity over billions of years. Regions that were slightly denser pulled in more matter and became even denser. Regions that were slightly less dense lost matter and became emptier. The result is the cosmic web we see today. The implications of this structure are profound. It tells us that the universe is not uniform. It's not the same everywhere. There are preferred locations where galaxies cluster, and there are empty regions. The universe has structure and organization on the largest scales. This also means that our location in the universe is not special. There's no center of the universe. The expansion of the universe looks the same from every point. No matter where you are, if you look out far enough, you'll see a similar cosmic structure. You'll see your own local voids and your own local filaments. The universe is homogeneous on the largest scales, but it's lumpy and structured on smaller scales. Let's talk about some of the things we've actually discovered about distant objects using light. When we observe a supernova, we're watching a star violently explode. For a few weeks, that explosion can be brighter than an entire galaxy containing billions of stars. And we can see supernovae from incredibly far away. In 2019, we detected a supernova in a galaxy called ASASSN 19LH. We're still not entirely sure what it was, but it's one of the brightest supernovae ever observed. It was so bright that despite being billions of light-years away, we could see it from Earth. We were seeing a stellar explosion that happened billions of years ago. The light from that explosion had been traveling through space and time for billions of years before reaching our telescopes.
When we observe planets around other stars, called exoplanets, we're doing something even more remarkable. We can't see these planets directly. They're too small and too dim compared to their host stars. Instead, we use indirect methods. One of the most successful methods is the transit method. We watch the light from a star, and when a planet passes in front of that star, the light dips slightly. The planet blocks a tiny fraction of the star's light. By measuring the dip, we can determine the size of the planet and the length of its orbit. Thousands of exoplanets have been discovered this way. We've found planets in the habitable zone of their stars, where temperatures might allow liquid water to exist on the planet's surface. We've found planets orbiting close to their stars, planets orbiting far from their stars, planets in binary star systems, and planets in all sorts of configurations. And all of this knowledge comes from analyzing the light from distant stars. We're not visiting these systems. We're not sending spacecraft there. We're analyzing light that's traveled light years to reach us. And from that light, we're inferring the properties of planets we can't directly see. There's something almost magical about this. We're limited by the cosmic speed limit. We can't travel to these distant worlds. We can't send spacecraft that would take tens of thousands of years to arrive. But we can analyze light. We can learn about distant worlds by studying their light. We can discover their planets, measure their properties, and determine whether they might be habitable. In 2020, astronomers detected a signal from Proxima Centauri, the nearest star system to us.
The signal appeared to be coming from a planet orbiting Proxima Centauri every 11.186 Earth days. This planet, called Proxima Centauri D, is much more massive than Earth, possibly a mini Neptune or super-Earth, and it's only 4.24 light-years away. But even though it's the closest planet to us, orbiting the nearest star, we have no way to reach it in any reasonable time frame. With current technology, it would take more than 70,000 years to get there. And that's assuming we devoted enormous resources to a mission that would take 70,000 years and would probably require multiple generations of spacecraft and space travelers. And yet, we know about Proxima Centauri D. We know it exists. We know its orbital period. We know its minimum mass. All of this information came from analyzing light that's been traveling for just 4.24 years. We've bridged the gap of 4.24 light years using light itself. This is one of the great paradoxes of astronomy. We can see incredibly far, but we can't travel far. We can observe the universe to distances of billions of light years, but our spacecraft can barely reach beyond our solar system. We can learn about exoplanets in other star systems, but we can't visit them. Light years are barriers that light can cross, but matter cannot. Let's take a journey through cosmic time, using light years as our measure. Imagine we're starting here on Earth, looking outward. At 1.3 light seconds, we reach the Moon. That's where humans went in the 1960s and 1970s. It's the farthest we've traveled in person. At 8 light minutes, we reach the Sun. This is where solar physics is done. The Sun has been observed continuously for decades. We know its composition, its structure, its behavior. And yet, even though we can study it extensively, the light entering our telescopes is 8 minutes old. We're always seeing the Sun as it was 8 minutes ago. At about 5.3 light hours, we reach the outer edge of the solar system. This is where the Voyager spacecraft are heading. They'll take tens of thousands of years to complete the journey. At 4.24 light years, we reach Proxima Centauri. This is the nearest star system. It has planets, as we've discovered, and it's impossibly far away. At 25 light years, we're seeing stars in our local stellar neighborhood. These are stars we can observe in detail with our telescopes. We can measure their distances, determine their compositions, and study their behavior. At 100 light years, we're beyond the reach of our current spacecraft for thousands of years. The light from stars at this distance took 100 years to reach us. At 1,000 light years, we're seeing a significant portion of the Milky Way's disk. We're seeing stars from the spiral arms of our galaxy. The light from these stars has been traveling since the medieval period on Earth. At 26,000 light years, we're approaching the galactic center. This is where the supermassive black hole Sagittarius A star is located. The light from this region has been traveling since the ancient Egyptian civilizations were building pyramids. At 100,000 light years, we've crossed the entire Milky Way. This is our galaxy's extent. To reach from one edge to the other, traveling at light speed would take 100,000 years. At 2.5 million light years, we reach Andromeda.
This is our nearest large galactic neighbor. The light we see from Andromeda left that galaxy when early humans were just beginning to craft tools. At 50 million light years, we're starting to see many other galaxies. We're seeing galaxies in various stages of evolution. The light from these regions has been traveling for tens of millions of years. At 300 million light years, we're seeing distant galaxy clusters.
The Virgo cluster and other nearby clusters are visible. The light from these regions has been traveling since before the dinosaurs evolved. At 1 billion light-years, we're seeing a significant fraction of the observable universe. We're seeing galaxies as they were a billion years ago. By this point, some of the most distant galaxies we can see are so far away that they're receding from us faster than light can travel toward us. At 13.8 billion light-years, we're approaching the edge of the observable universe. We're seeing the universe as it was just a few 100 million years after the Big Bang. We're seeing some of the first galaxies that ever formed. At 46.5 billion light-years, we've reached the edge of the observable universe. This is the farthest we can see. The light from this distance has been traveling for 13.8 billion years, but the objects themselves are now much farther away due to cosmic expansion. This journey through cosmic time and distance shows us the enormity of the universe and how far our telescopes can reach. But it also shows us our limitation. We can see to the edge of the observable universe, but we can't travel there. The cosmic speed limit prevents us from visiting distant worlds. We're confined to a small corner of the cosmos, looking outward through the lens of light. Part 7. The Physics of Light Years. Let's dive deeper into the physics of light years and what they tell us about the universe. Light, as we've established, travels at about 186,282 miles per second in the vacuum of space. This speed is not arbitrary. It emerges from Maxwell's equations, the laws of electromagnetism. Light is an electromagnetic wave, and the speed at which it propagates is determined by the properties of the vacuum itself. Einstein showed that this speed is the maximum speed at which information can travel. Nothing can exceed the speed of light. This is not because we haven't built a fast enough rocket. It's a fundamental property of space-time. As objects approach the speed of light, their mass appears to increase. The faster an object goes, the more energy is required to accelerate it even slightly. At the speed of light, infinite energy would be required to accelerate any massive object even slightly. Therefore, massive objects can never reach the speed of light. Light itself is massless, so it can travel at this ultimate speed. In fact, light must travel at this speed. It can't go slower. Light propagates through the vacuum at exactly the speed of light, no more, no less. This has profound implications. It means that there is a cosmic speed limit. It means that information cannot travel faster than light. It means that no two events that are separated in space can have any causal relationship unless enough time passes for light to travel between them. In physics, we talk about the light cone. For any event, there's a forward light cone and a backward light cone. The forward light cone is the region of spacetime that can be causally influenced by that event. The backward light cone is the region of spacetime that can causally influence that event. Everything outside the light cone is causally disconnected from the event. This is why light years are important. They define the structure of space-time itself. They define what can communicate with what can influence what, and what's causally isolated from what. Now here's something fascinating. In Einstein's theory of general relativity, gravity is not a force in the traditional sense. It's the curvature of space-time. Massive objects curve the space-time around them, and other objects follow the curved paths which we perceive as the force of gravity. When we observe planets around other stars, called exoplanets, we're doing something even more remarkable. We can't see these planets directly. They're too small and too dim compared to their host stars. Instead, we use indirect methods. One of the most successful methods is the transit method. We watch the light from a star, and when a planet passes in front of that star, the light dips slightly. The planet blocks a tiny fraction of the star's light. By measuring the dip, we can determine the size of the planet and the length of its orbit. Thousands of exoplanets have been discovered this way. We've found planets in the habitable zone of their stars, where temperatures might allow liquid water to exist on the planet's surface. We've found planets orbiting close to their stars, planets orbiting far from their stars, planets in binary star systems, and planets in all sorts of configurations. And all of this knowledge comes from analyzing the light from distant stars. We're not visiting these systems. We're not sending spacecraft there. We're analyzing light that's traveled light years to reach us. And from that light, we're inferring the properties of planets we can't directly see. There's something almost magical about this. We're limited by the cosmic speed limit. We can't travel to these distant worlds. We can't send spacecraft that would take tens of thousands of years to arrive. But we can analyze light. We can learn about distant worlds by studying their light. We can discover their planets, measure their properties, and determine whether they might be habitable. In 2020, astronomers detected a signal from Proxima Centauri, the nearest star system to us. The signal appeared to be coming from a planet orbiting Proxima Centauri every 11.186 Earth days. This planet, called Proxima Centauri d, is much more massive than Earth, possibly a mini Neptune or super-Earth, and it's only 4.24 light-years away. But even though it's the closest planet to us, orbiting the nearest star, we have no way to reach it in any reasonable time frame. With current technology, it would take more than 70,000 years to get there. And that's assuming we devoted enormous resources to a mission that would take 70,000 years and would probably require multiple generations of spacecraft and space travelers. And yet, we know about Proxima Centauri d. We know it exists. We know its orbital period. We know its minimum mass. All of this information came from analyzing light that's been traveling for just 4.24 years. We've bridged the gap of 4.24 light-years using light itself. This is one of the great paradoxes of astronomy. We can see incredibly far, but we can't travel far. We can observe the universe to distances of billions of light-years, but our spacecraft can barely reach beyond our solar system. We can learn about exoplanets in other star systems, but we can't visit them. Light-years are barriers that light can cross, but matter cannot.
The nearest star is 4.24 light-years away. Even if we could somehow achieve 10% of the speed of light, which is a technology we don't have and can't foresee in the near future, it would still take 42 years to get there. That's a significant portion of a human lifetime. The interstellar distances are genuinely vast. But we have some reasons for hope. First, our technology is constantly improving. We don't know what discoveries might be made that could eventually enable faster travel. Antimatter propulsion, fusion propulsion, or even more exotic technologies might be possible in the distant future. Second, we don't necessarily need to travel to distant stars to explore the universe. We can continue to use light and telescopes to observe the universe. The next generation of telescopes will be even more powerful than the James Webb Space Telescope. The extremely large telescope, which is currently under construction, will have a mirror about 39 meters across, making it the largest optical telescope in the world. It will be able to see objects even more distant and fainter than the James Webb can see. We can also use other methods to explore the universe. Gravitational wave astronomy,
which has only recently become possible, allows us to detect gravitational waves, ripples in space-time itself, from events like the collision of two black holes or two neutron stars. These events happen billions of light years away, but the gravitational waves travel at the speed of light and can be detected on Earth. Neutrino astronomy is another emerging field. Neutrinos are ghostly particles that are produced in nuclear reactions and cosmic events. They pass through ordinary matter almost undetected, but instruments like the Ice Cube Neutrino Observatory can detect them. Neutrinos from distant cosmic events can reach Earth and tell us about those events. And we're always improving our ability to analyze light. New spectroscopic techniques allow us to extract more information from the light we receive. New algorithms and computational methods allow us to process vast amounts of data and extract meaning from it. So the future of cosmic exploration, at least for the foreseeable future, will rely on light and light years. We'll study the universe by analyzing the light that reaches us. We'll use telescopes and detectors to gather information about distant objects. We'll use light years as our ruler to measure the universe. And that's okay, because light is an incredibly powerful tool. Through light, we can see across billions of light years. Through light, we can understand the history of the universe. Through light, we can observe cosmic events that would be impossible to witness in person. Part 10. The Fermi Paradox and the Great Silence. We've talked about the vastness of the universe and the isolation created by light years. This brings us to one of the greatest puzzles in science, the Fermi Paradox. The basic question is simple. If the universe is so vast, with billions of galaxies, each containing billions of stars, and if many of those stars have planets, and if some of those planets might harbor life, where is everybody? Why haven't we detected signals from...
Why is the universe so silent? There are several possible answers to this puzzle, and many of them involve light years. One possibility is that the universe is simply too big. The distances between habitable planets are so vast that communication between them is nearly impossible. Even at the speed of light, messages would take years or centuries or millennia to arrive. Civilizations might arise and fall before ever establishing contact with other civilizations. The sheer distance creates isolation. Another possibility is the Great Filter. The Great Filter is the idea that somewhere in the process of a civilization developing from the origin of life to a spacefaring civilization, there's a very difficult step. Perhaps life is rare. Perhaps intelligent life is rare. Perhaps stable, long-lived civilizations are rare. Whatever the Great Filter is, it's preventing civilizations from reaching the point where they can communicate across light. Why is the universe so silent? There are several possible answers to this puzzle, and many of them involve light years. One possibility is that the universe is simply too big. The distances between habitable planets are so vast that communication between them is nearly impossible. Even at the speed of light, messages would take years or centuries or millennia to arrive. Civilizations might arise and fall before ever establishing contact with other civilizations. The sheer distance creates isolation. Another possibility is the Great Filter. The Great Filter is the idea that somewhere in the process of a civilization developing from the origin of life to a spacefaring civilization, there's a very difficult step. Perhaps life is rare. Perhaps intelligent life is rare. Perhaps stable, long-lived civilizations are rare. Whatever the Great Filter is, it's preventing civilizations from reaching the point where they can communicate across light years. Another possibility is that civilizations eventually destroy themselves.
Perhaps the development of advanced technology always leads to war or environmental collapse. Perhaps civilizations are self-limiting, reaching a certain level of advancement and then destroying themselves before they can spread to other stars. If this is true, then we might be one of the few civilizations that survives long enough to wonder about the silence. Another possibility is that we're simply not looking in the right way. Perhaps alien civilizations communicate using methods we haven't thought of. Perhaps they use technology so advanced that we can't recognize their transmissions. Perhaps they're deliberately hiding from us. Perhaps they're using methods of communication that don't involve electromagnetic radiation at all. Another possibility is that we're early. We are one of the first technological civilizations in this region of the galaxy. The universe is old, but intelligent civilizations might be rare, and there might simply be no one else out there yet, at least not nearby. Or perhaps we're late. Perhaps all the civilizations that were nearby have already expanded and colonized the galaxy. Perhaps we're just being ignored because we're not very interesting. Perhaps we're in some kind of cosmic zoo, and advanced civilizations have simply decided not to interfere with us. All of these possibilities involve the vast distances measured in light years. Because of those distances, civilizations are isolated. They can't easily reach each other. They can't easily communicate. The universe is too big, and travel and communication are too slow. And this brings home the fundamental insight. Light years are not just astronomical measurements. They're limitations on communication, on exploration, on the possibility of a unified galactic civilization. They're the cosmic distances that define the possible futures of intelligent life in the universe. Part 11. Black holes and the limits of light. Light years also help us understand some of the most extreme objects in the universe, black holes. A black hole is a region of space-time so heavily curved that not even light can escape from within a certain boundary called the event horizon. The first black hole was theoretically predicted by John Michell and Pierre-Simon Laplace in the 18th century, but Einstein's theory of general relativity provided the modern understanding of black holes. In Einstein's theory, a sufficiently massive star can collapse at the end of its life, compressing all its mass into a point of infinite density called a singularity, surrounded by an event horizon. Now here's something fascinating. If you were to fall into a black hole while holding a flashlight, the light from your flashlight would be bent by the intense gravity. The light would follow curved paths around the black hole. Some of the light would eventually escape and travel outward through space. But as you got closer to the event horizon, less and less of your light would escape. Once you crossed the event horizon, no light would escape at all. You would disappear into a region from which no information could escape. This is why black holes are so interesting for studying light years. Black holes bend space and time so extremely that they demonstrate the limits of light's ability to escape from gravity. They show us that in certain circumstances, the light we depend on to explore the universe can be trapped and prevented from reaching us. The black hole at the center of our galaxy, Sagittarius A, is about 4 million times the mass of the Sun. It's about 26,000 light-years away.